So welcome back to talking about parallel FFTs. And this is one of the last motifs or dwarfs that we're going to talk about. So far this semester, we've concentrated on talking about everything in here for which you see a red brick, which means it's heavily used in HPC. So dense matrices, sparse matrices. We talked about n-body, we talked about unstructured grids, and today we're going to talk about how to do FFTs in parallel, or things that are very similar to FFTs. And so I'm going to start from scratch and don't assume that you know anything about FFTs, but I'll do it quickly, remind you of how the basic algorithm works, a divide and conquer, and show you a few applications, tell you the sequential algorithm, then how to parallelize it, and also minimize communication. So I'll talk about the parallel 1D FFT. And it turns out that a lot of the same ideas apply to high dimensions. So I'll do a fairly in-depth dive in how do we do a parallel 3D FFT. Now, FFTs being so popular, they get auto-tuned. And people have been, there are two organizations, two groups that have been working on auto-tuning FFTs for quite a while, and almost everybody uses their code, at least for the 1D case. So one of them is called FFTW, the fastest Fourier transform in the West. And I'll give you a little show of how they do their auto-tuning. And Spiral is another one, which aspires to do actually all of signal processing. So much beyond FFTs. So and there are lots of references for this stuff as well. But let's start at the beginning and talk about how FFTs work. So I'm going to try to let I never be an index during this lecture, only ever equal the square root of -1, so we can keep that straight. And all of my arrays are going to be indexed from 0. And so the one-dimensional discrete Fourier transform is a nice, simple matrix vector multiply with this very special matrix. Its entries are powers to the jkth power of a root of unity. So there is a number, omega, whose mth power is 1, right? And that's what I want to do a matrix vector multiply. And if I did it the obvious way, it's n by m, it'd be m squared. I want to do it in m log n. So, but I also am interested in doing it in higher dimensions. So let me just define all those now while I'm at it. So what's a higher dimensional FFT? What's the two-dimensional FFT? Well, I can write it this way as a matrix product. What does the multiplication by f do? It basically does the FFT of each column independently. And then what do I do when I post-multiply by f? That does the FFT of each row independently. So that's what a two-dimensional FFT is. And I can do, and since multiplication is associative, I can either do all the rows first and then all the columns, either way. And for higher dimensional FFTs, which is what I'm going to sort of dive into later, it's the same idea. Suppose I have a cube, a three-dimensional array of data, an m by m by m array. I'm going to do the FFT of each vertical slice, say in the x direction, each of those vectors independently. There's m squared of them. Then I'll do all the FFTs in the y direction, all m squared of those independently. And then all m squared in the z direction. That's what a three-dimensional FFT is, which we are going to talk about. And of course, you can do it in any dimension you want. So, and please stop if you have questions here. So, yes? It would be done with tensors or Kronecker products. And so I'm not going to try to write down that notation. If I wanted to, I will show you how to solve Poisson's equation using the FFT. And that will, but I'm only going to do it in 2D, so I only need this notation here, which is the matrix vector, the matrix multiply. But you can solve Poisson in 3D using the FFT just as well, but I probably won't do all the I don't think I'm going to do all the algebra. I can do it for you later. So here are the classical applications. I'll just show you a few. Signal processing, image processing. If you know anybody who's ever looked at a JPEG image, you know somebody who uses the FFT, so that's a lot of people. The Poisson equation, and which I'll talk about in a little more detail. Fast multiplication of large integers, that's the fastest known algorithm. And if you Google FFT, you can find a few thousand other applications of it. So, but let me just show you two, just for, to remind you. This is the simplest signal processing application that you can imagine. I'm going to take a signal. It's a sum of two sine curves, sine 7t plus 1/2 sine 5t. A nice simple, there it is, nice wavy line. And what I want to do is add noise to it, a lot of noise. I'm going to add a random number to every point in the signal of size 0.75, and I get this totally jagged thing. And I want to extract out, filter out all that noise and get back to the original signal. So the FFT is classically done. What do you do? So let me take the original signal and take its FFT. I get a complex answer. So here's the real part. It's all 0. And here's the imaginary part. And it's only non-zero in two places, corresponding to frequency 7 and corresponding to the frequency 5. So only get those little spikes right there. So what do I do when I add the noise and take the FFT? I get a bunch of noise spread out over the real part, and I get a bunch of noise spread out over the imaginary part. Now, these two are pretty similar. I can sort of see how to get rid of that noise. And over this here, it's pretty similar. So what am I going to do? I'm simply going to take every component of these two vectors, the real part and the imaginary part, and throw away all the tiny numbers. Anything less than, say, less than a quarter. When I do that, all that turns to 0. All the stuff in the middle turns to 0. And I do the inverse FFT, and it looks indistinguishable. So I filtered out all the noise. This is sort of the classical use for FFTs. In one dimension, let me do the same thing in 2 dimensions. So here is a typical 2-dimensional matrix, right? The same thing. So each entry has a color associated with it. It's 200 by 320. So what I'm going to do, I'm going to compress it. I'm going to take its 2-dimensional FFT, which is a 200-dimensional FFT in the vertical direction and a 320 FFT in that direction, and I get a new matrix. And what I'm going to do is compress it. How am I going to compress it? I'm going to throw away all the tiny numbers. The same thing I did in the previous one. I'm only going to keep the largest 2.5% of the entries of that 2-dimensional FFT. And then I'm going to do the inverse, and I get back sort of a clown. OK, so probably 2.5% isn't enough. But this is how JPEG works. It takes FFTs of little 8 by 8 blocks of each image, and it compresses it by using very few bits for each number. And it's good enough for most of the purposes that we have on our screen. Here's just sort of a blown-up version. And finally, let's go back to Poisson and talk about how FFT works with Poisson. And you've heard enough about Poisson in this class already. There's the one-dimensional equation. There's the two-dimensional equation. I have second derivative with respect to x and y. And there's the three-dimensional one, second derivatives with respect to x, y, and z. And it comes up in all sorts of different modeling problems. I'm just going to do the most basic ones. So let me just remind you what the matrix form of it is. And then I'll show you how to solve it really fast with the FFT. So I need to write down the one-dimensional equation and the two-dimensional equation. So there's the one-dimensional Poisson equation. L1 times x equals b. I got to solve that for x. L1 is just a derivative in the x direction. And so it's this nice, simple tridiagonal matrix. It's a stencil, 2 times each entry and -1 times the neighbors. That approximates the second derivative. And I don't need the FFT to solve that. That's too easy. But I need that to build the two-dimensional FFT. So here's the two-dimensional FFT matrix. And it's this matrix times a vector, and I want to solve that for x. And so this basically says it's a derivative in the x direction, -1, 2, -1. And then I add the derivative in the vertical direction, -1, 2, -1. So I get 4 on the diagonal. And I want to solve that. And now it's no longer so obvious. And we spent a while talking about multigrid and various other clever algorithms to do it. But I'm going to solve this with the FFT really fast. So here's how it works. So it's going to use a special relationship between this matrix, L1, and the FFT. Or more precisely, the imaginary part of the FFT. That's good enough. So there's the L1 matrix. That's the second derivative. And it turns out I can write down its eigendecomposition. It's explicit eigendecomposition. So there's the matrix whose columns are the eigenvectors. It's the FFT, the imaginary part of the FFT. There's the diagonal matrix, eigenvalues down the diagonal. Nice, simple closed formulas for it. And there's the inverse of the eigenvector matrix, which is just the transpose, because it's an orthogonal matrix. OK, so that tells me that Poisson and FFT are very, very closely related. So now the question is, how do I use that relationship to solve the two-dimensional one? So let me write down 2D Poisson in this way so that I can sort of use this notation you asked about earlier, which is I can just write it using matrix multiplies. So this is multiply L1. So x is a m by m array of my unknowns where I want to solve for it. So I'm given b, and I want to solve for x. So this says take the derivative in the y direction of each column. And this says to each row, multiplied by L1, take the derivative in the x direction and solve that. So here's the idea. I'm going to take L1, and I'm going to substitute it into this equation. I'm going to use the fact that L1 has this eigenvalue decomposition. And that's going to make this system of linear equations diagonal. I know how to solve a diagonal system of equations. That's not hard. So here's how it works. I'm going to take my right-hand side b, and I'm going to do the 2D FFT on it. So I'm going to do the FFT on all the columns and all the rows. So both of these are really fast. Now when I plug that back into here, what does my equation turn into? It turns into diagonal matrix times unknowns plus unknowns times diagonal matrix equals my new right-hand side. This is a diagonal system of equations. It's trivial to solve. All I have to do is take each b and divide it by some number, sum of eigenvalues, to get each entry of x prime. So I've solved the diagonal one. So now I just have to go backwards and go from x prime to get x, 2 more FFTs, one more two-dimensional FFT. And if you plug all this algebra together, I basically solved that one. Right? Just changed basis so it's all a diagonal. And so what was the cost? I did one 2D FFT. Then I did a bunch of n squared adds and n squared divisions. And then I did another 2D FFT. So the whole thing, once I show you how to do FFTs fast, cost me n squared log n. And this is a good way to do it. It's competitive with multigrid. It's not clear which one wins. Kind of depends on the size and the computer and all that kind of stuff. And 3D is analogous, but I won't try to write down all the algebra. But it's the same idea. You do 3D FFTs, get a diagonal system, then 3D FFT. And that explains, well, are there any questions about this? So this is all I'm going to say about Poisson, and I'm just going to concentrate on how do you do the FFT now. Okay. So, and this explains this row in this table, which I've shown you many times during the semester. This is the list of all the algorithms we've been talking about for doing linear algebra sorted in order of how fast they solve Poisson's equation. And there's the FFT running in n number of unknowns, log n time, almost hitting the lower bound. And so now that we know that, we're going to go back and say, how do we do the FFT? And do it fast. So let me say that there's a lot. I'm only going to talk about one flavor of the FFT. When I did Poisson, I said, oh, I'm just going to take the imaginary part. So all the algebra is about the same. To keep things simple, I'm just going to do one FFT, the one with the complex numbers in it. Keep it simple. So you notice that I had to multiply both by f and f inverse, or f transpose, in all those algorithms. That's really easy if I know how to multiply by f. How do I multiply by f inverse? It's just the complex conjugate and divide by m, right? So it's the same algorithm. So that's not hard. And sometimes I have to multiply by the imaginary part. Some people call that the sine transform because the imaginary parts are sines of angles. Some people, for I think jpeg uses the cosine transform. That's just the real part. I mean, so all the algorithms work the same way, but I'm just going to keep it simple and talk about the complex case. Okay. So let me just tell you what the serial algorithm is, remind you how it works, and then we'll go on to parallelize it. So to derive it in just a couple of slides, I'm going to show you that doing the FFT is really evaluating a polynomial. And I'm going to do a divide and conquer algorithm that evaluates this polynomial. So here it is. This is just the expression, what's a matrix vector multiply, the dot product of the jth row of f with my vector of inputs v. Plug in the formula for what is the jkth entry of f. It's the root of unity to the jkth power. Put in some parentheses and recognize that what am I doing? I'm evaluating a polynomial. The input vector are the coefficients, v1, v2, and stuff. And where am I evaluating the polynomial? At the jth root of unity. So I'm evaluating the polynomial, this polynomial, at the 0th root of unity, j equals 0, the first root of unity, at j equals 1, j equals 2, j equals 3. I'm evaluating it m times. That's what I need to do. And the polynomial coefficients are the inputs. Okay, so I want to do divide and conquer. And divide and conquer means I have a problem of size m. I want to divide it into two problems of size m over 2. And then life is good. I get n log n at the end. So how do I take that problem of I have a degree m polynomial. I want to evaluate it at m points. And I want to break it into two problems of half the size. Okay, so here's the polynomial again. Let me just write it down. And at this point, I'm going to do something that's true for every polynomial. It has nothing to do with the FFT. I'm going to take the even-numbered terms and the odd-numbered terms. That certainly breaks into two problems of half the size. So there's the even coefficients. So I get x squared, x to the fourth, x to the sixth. And there are the odd ones. I get x, x cubed, x to the fourth. Let me just factor out a common factor of x. So now I get two polynomials, v even with the even coefficients, v odd with the odd coefficients. And they're evaluated at x squared. Right? So there's an x squared, x to the fourth. So I can think of them as polynomials in x squared. And so this is now a polynomial of half the degree. And that's my problem of half the size. So there I have two polynomials of half the degree. But I'm not quite there yet. because I also only want to evaluate them as half as many points, right? To make the problem half as big, I have to have half the degree and half as many points. So how do I do that? Well, what I recognize is when I square all these numbers, what am I doing? I'm taking all these roots of unity, omega to the 0, to the 1, to the 2, to the 3, and I'm squaring them to evaluate them. And the magic is that when I square them, I only get half as many distinct points. So when I take all these different roots of unity and square them, they pair up, and because they come in plus minus pairs. And so whenever I have one of these guys equaling something, I also get the negative. So when I square it, they match. And so when I square them, I only get half as many as I had before. And so here's the algebra. Suppose I square omega to the power j plus m over 2. I square it. And so I just do law of exponents, break it up this way, and I get a factor of omega to the m out. What's omega to the m? Omega is the mth root of unity, so it's 1, and so it's the same as squaring omega j. So omega j and omega j plus m over 2 square them, I get the same numbers. So I actually only have half as many arguments to evaluate them at. So my problem of evaluating this polynomial on m points is now reduced to 2 polynomials, half as many coefficients, half as many points. So that's my divide and conquer algorithm. And so let me write it all down on one slide. Here it is. Write a little simple recursive algorithm. I'm going to call the FFT. I'm going to pass in the vector of coefficients, pass in the root of unity, and pass in m. I don't actually need both, but just to make it obvious what's going on. So there's a dimension. If I'm doing a 1-by-1 problem, we'll just do it. There's nothing to do. Just return v0. Otherwise, I take the even-numbered coefficients, v sub 0, v sub 2, etc., evaluate it not at that argument, but at that argument squared, and remind myself it's a problem of half the size. I do the same thing with the odd-numbered ones, so v sub 1, 3, 5, 7. Same omega squared. So now, now I've gotten all these numbers. I've gotten all those numbers. I've gotten all those numbers. I have to do the arithmetic with the plus and the multiply now. So I take all the values of x that were on the previous slide. That turns out to be this vector of powers of omega, and I can pre-compute that. That's just lying around. And now I take each one of these numbers and I multiply them by those. This is MATLAB notation. So this vector gets component-wise multiplied by that vector. So I'm doing all of these multiplies for all the values of x times v odd of all the corresponding values of x squared. And then and for some of them I add, and for some of them I subtract. So let's go back here and look. So I'm just evaluating this formula for all the different x inputs. But remember, some of the x's, for every x I get negative x, so that x squared is the same. So when I get plus x and minus x, it's the same product, right? All that differs is whether I add or subtract. If I change x to minus x, that number stays the same, that number stays the same, and all I do is subtract instead. And that's what's going on here. I either add or subtract with the same product. And so there's the whole algorithm. And so now I can write down the complexity. The time to run this algorithm of size m is 2 problems of size m over 2. And then I do another m multiplies and m adds, call that order m, and there's the cost. Yes, and let me give you the microphone.
Where are you saving time? It seems like you're evaluating both the odd and the even components anyway. So.
Right, and that's why I have a 2 here. So I have 2 problems, 2 FFTs of half the size. So do you agree that this formula captures the cost of that algorithm? So are you saying why is the solution of this just m log m?
I'm saying what saves you time?
Why is this not m squared? Because the naive algorithm would have been m squared.
Okay. I'm sorry.
And now I'm down to m log m.
Okay.
That was the goal.
Okay.
Right. Does Nick want to add a comment?
You did fewer additions and multiplications.
Yes. Yeah, many fewer, right? We went from m squared down to m log m.
If you write down the FFT matrix and look at its structure and look at subset sums of different rows, you'll see that some subset sums match in different rows. So doing dot products with rows and columns, you can avoid some of that work. And
that's exactly what's expressed in this nice divide and conquer algorithm. Yes. So this is nice, but now we have to sort of look at this structure a little bit more carefully to figure out how to parallelize it. Okay. So what I'm going to do is draw the call tree of this algorithm. So every time I call it, I get 2 calls to submatrices. Each of those turn into 2 more calls. I just want to look at that binary tree of all the calls and understand what data depends on what other data. Because that's going to sort of be where I spend most of my time worrying about the algorithm, making sure the data is in the right place at the right time. So here, I'm just going to draw every last detail for the case of m equals 16, because that's a reasonable amount to look at. So here it is. So I'm going to call my FFT on a vector of size 16. And what I've written in here is all the subscripts of all its arguments, v sub 0, v sub 1, v sub 2, up to v sub 15. And the reason I've chosen a nice power of 2 is that I can also say that all the arguments here, 0 through 15, how do I write down all those numbers? They're just binary numbers that are 4 bits, and every bit can be whatever you want. Each x can be a 0 or a 1. If they're all zeros, I get 0. If they're all 1s, I get 15. And for every combination of x being 0 or 1, this is just how I would express that. So now, if I look at the algorithm, I got to call FFT on the evens and the odds. How do I tell whether a number that looks like in binary is even or odd? Well, that's pretty easy. I look at the last bit. And so when I call FFT in the even part, I just pass in the arguments whose last bit is 0. Those are the even ones. And for the odd ones, I just look at the ones whose last bit is 1. So I get these 2 calls, f in the even, f in the odds. But it's recursive. So what do I do now? I need to take, here are all my arguments. I have to pick every other one. I have to take the even ones out of this. So I need to take 0, 4, 8, 12, stuff like that. How do I look at this number and decide whether I'm even or odd? Yeah, look at the next bit. Is the next bit 0? Or is it 1? There's the 0, that's the even. There's the 1, and there's the odd case. So every divide and conquer step here, I just look at the next bit and say, are you 0? Go left. Are you? And that's what the divide and conquer tree looks like in the call tree. So let's go all the way to the bottom, and where I finally run out of bits. So I have 4 levels, 4 bits. And finally, I get to the case where I've called the FFT on a scalar, and it actually is done, right? It just sort of returns. So at this point, the scalar is so here the bit is 0, so everything's been even, so it's all zeros. Here, the last bit is 1, so I get an 8. It's 1, 1, 0, 0, that's a 4. And then 1, 1, 0, 0, that's a 12. So all these bits at the bottom, these consecutive guys, these neighbors, they all differ in the first bit. They differ by 8. So I combine 0 and 8, 4 and 12, 2 and 10. So those are far apart, in the original array. So I'm going to have to worry about that. Here's the other thing to notice. Look at the order in which the outputs, in which everything appears. 0, 8, 4, 12, 2, 10. That's not 1, 2, 3, 4, right? That's a different order. So what is the order? This is all bit 0, and then 1, 0, 0, 0. This is 0, 1, 0, 0, and then 1, 1, 0, 0. So what do these bit patterns? So what if yeah. Anybody want to venture a guess? Nick, behind you. The answer's in red on the slide.
Yeah, if you reversed the bits, then it would be counting up.
Bit reversed order. So when you run this algorithm and you look at the output, it comes out in bit reversed order because of this pattern that you see here. And so it's scrambled. And that's something you have to deal with. So, but the good news is if I now do the inverse FFT, and I reverse it twice, I get back the right order. So a lot of algorithms are perfectly happy. You do an FFT, you do some filtering, you do an inverse FFT, and you get back everything in the right order. So, but it comes out scrambled in the middle. That's just something to think about in the algorithms. I won't worry about it too much. OK, so now let me use this particular insight. So what's the insight? At the bottom level, I'm combining things that differ by 8. 0 and 8, 4 and 12. At the next level, it's the next bit that differs. So they differ by not 8, but 4. At the next level, they differ by 2. At the next level, they differ by 1. So that's sort of the communication pattern. And I'm going to draw, again, for 16, every last detail. So here's a picture of every last detail of who talks to whom. And so here's all the inputs numbered from 0, 0, 0, 0 up to 1, 1, 1, 1. And here's the next layer of values that are computed when I do one multiply and one add. And there's the next layer. So each one of these is a layer in the recursion tree. So, and these edges say who depends on whom. So in particular, that number, that little dot there says, and that edge says, please take the vector entry 0, 0, 0, 0 and combine it with the one who's numbered 1, 0, 0, 0. Combine 0 and 8. And this one says also combine 0 and 8, but do it with a negative instead of a plus. And so this little black butterfly, this is called the butterfly FFT because you can see a lot of butterflies in this picture, right? Because that's the dependency pattern that gets repeated over and over again. So 0 gets combined with 8 for that little butterfly. The next red-colored butterfly, which you can almost see, is 1 and 9. The next green butterfly is 2 and 10. And so at this first level, where everything divides by 8, I get these butterflies whose wingspan is 8. The next level, the numbers differ by 4. So I get lots and lots of butterflies again, but their wingspan is now 4. So I combine 0 with 4. 0 with 4. I combine, there's the red butterfly. I combine 1 with 5 and so forth. And now notice, when I do that, there's no communication from that top part to that bottom part. I'm going to take advantage of that momentarily. The next layer, they differ in the second bit, so I only move 2 down. The butterflies only have a wingspan of 2. And the last level, they only have a wingspan of 1. So that is the general pattern that I need to figure out how to parallelize. That's sort of every last detail of the algorithm. And for n equals 16, it's kind of visible what's going on. But you can imagine scaling it up. OK, so now the question is, I want to run this in parallel. And I'm going to, let's say, just do 4 processors, keep it easy. I have to decide which processor is responsible for which entries of the vector and which computations. And if you remember from when we did matrices, there were 2 natural ways to lay out a matrix. If I just, a one-dimensional layout. So what's the obvious layout? The simplest one you could imagine. Blocked, right? So I'm just going to block it. And so if I have 4 processors, each processor will get the first 4, then the next 4, then the next 4, and the next 4. I'll show you that one in the next slide. But there was another layout that we talked about that was also useful for some matrix operations. How else could I deal out the vector entries to 4 processors? What did we call it? Besides block, there was cyclic, right? So processor 0 gets the first one, processor 1 gets the second, processor 3 gets the third, 4, and then I go back to 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. I could deal them out like a deck of cards, cyclic. So let me look at both of them and see which one, see what the communication looks like. We'll do blocked first. OK, I have 4 processors numbered 0 through 3, and they're all color-coded. So processor 0 is going to be responsible for this part of the graph and doing all the arithmetic and stuff. And he's going to start by owning just those 4 entries. And processor 1 is going to be responsible for everything in the blue box, and he's going to start with owning those entries. And it's the same butterflies, but I've done color coding now. And the idea, the way I've color coded it is if this guy depends on 2 pieces of data, follow the edges, in 2 different processors, if he requires communication, I've colored him black. OK, so all of these guys touch 2 different processors, and it's communication. The next layer, again, there's communication. But what happens when I get here, and I'm only going a distance 4 away? My wingspan of my butterflies has shrunk to 4. I stay in the same processor. There's no communication there. So I've colored him green, because the green processor can do it all by himself with no communication. And the next layer, it's the same thing. It's only 2. Again, the green processor can do it with no communication. And so from this layer on out, there's no communication. And from this layer up to there, it's all communication. So, and this I hope is easy to see. I have 16 processors, 16 points, 4 processors. Now, what's the general rule? Suppose I have m points and p processors. How many layers do I do communication, and how many layers do I not? So the answer is down here in small font. So for the first, so I'm going to keep doing communication until I don't have all the bits. I look at the first bit, and that's the 8. That tells me to go 8 away. Then I look at the next bit. It's a 4. It tells me to go 4 away. So as soon as I don't have to go far enough away and I'm in the same processor, I'm done. That's log p steps. You can sort of count bits. That's how many steps you have to take. And the last log m over p steps, because there's a total of log m steps, there's no communication at all. Okay, so that's the blocked layout. The next one I was going to say is cyclic. All right, want to venture a guess as to what it looks like? Just reverse when you do the communication. Okay, so this is a cyclic layout. Processor 0 owns every fourth entry. Processor 1 owns every fourth entry, and so on. So now, when I take that bit and I flip it from 0 to 1, and I go 8 away, processor 0 owns that. Oops, sorry. Processor 0 owns it. And when I flip this first bit, and it's processor 1 owns it, so I go from 0001 to 1001, follow the butterfly, and again, processor 1 owns it. So there's no communication there at all, and I've colored it accordingly. So when there's colored edges, that means the green processor owns it all, there's no communication, and there's only communication in the trailing edges. They're all colored black to indicate that. So again, there's no communication in log m, the first log m over p steps, but there is in the last log p steps. So I want to have the best of both worlds here. But let me just write down a performance model for these two algorithms, because it's the same performance model for both of them, because they both have the property that they communicate for log p steps, and they don't communicate for log m over p. That's all I need to know to write down the cost. So let me write down the complexity, really simple. It's going to be vectors of size m, p processors. Assume everything's a power of 2 to keep it nice. F will be the time per flop. I'll assume that's 1. Alpha is the latency, and beta is the time per word in a message. So I'm going to do my usual latency bandwidth model. So the time for either one of those algorithms, whether I lay it out in a block or lay it out cyclically, is the parallelism is perfect. I'm doing 2m log m floating point operations, and every processor gets 1/10 of it, so that's a perfect layout. I have log p levels in which I have to communicate, so there I have log p messages. So that corresponds to all these guys here. There's only log p of those layers. So there's log p alpha, latency cost. And then how much am I actually sending? Well, every processor has to send everything it owns to somebody else, basically, in those last layers. And so everybody has to, so that's m over p, and there's log p layers, so it's m over p log p times the reciprocal bandwidth. So that is for both. So the question is, can I do any better? So how do I combine that picture where I don't communicate at the beginning and that picture where I don't communicate at the end? So what's the obvious thing to do? I want to change layouts in the middle. So I want to go from this cyclic layout at the beginning to a blocked layout at the end. All right? And this is what it looks like. I start with a cyclic layout, and I transpose the data to switch from a cyclic layout to a block layout. And then I do no communication anymore. Okay? So I've sort of put all the communication into the middle in this operation called a transpose. I'll explain why it's called a transpose. So again, there's no communication at the beginning. All the cost is in there. And then there's no communication at the end. And I'm sort of assuming, to keep this picture simple, I'm assuming that log m over p equals log p. But it gets a little more complicated if it doesn't work out that way. But it's the same idea. I do a transpose in the middle somewhere. OK, so the question is, why do I call this a transpose? So here I've shown you the block layout for the same problem. And here I've shown you the cyclic layout. So the block layout is the green processor. Processor 0 owns the first 4 vector entries. Processor 1 owns the next 4. Processor 2 owns the next 4. Fine. Here's the cyclic. Lay them out so that processor 0 owns every fourth. Processor 1 owns every fourth. But consecutive ones are in different processors. Now, look at this 4x4 array of numbers and compare it to that 4x4 array of numbers. What's it look like? It's a transpose, right? I've transposed this matrix to get to that matrix, right? So this is, Nick? That's why we call this particular data operation transpose.
So you need to have a square number for
So
processors?
No, the pictures get more complicated, and I just haven't bothered to draw them all, but it can be done for general powers. So m can be any power of 2, and p can be any power of 2. And there might be more than one transpose step. But I'm just showing you the simplest case to give you the idea. Yes. OK, so now that's the algorithm. And what I want to do is write down again on one slide what its costs are. Write down a performance model. And I'm going to do it in two ways. The first one is going to be a sort of a pessimistic way, assuming that I can't pipeline any communication. And then I'll say what really happens. So again, the arithmetic is perfectly parallel. 2m log m, everybody gets 1/10 of it. Again, everybody has to send the same amount of data. They have to take everything they own, almost, and send it to somebody else. So m over p data sent to almost everybody else, p minus 1 over p. So this is smaller than what we had before by a factor of log p. So there's the big benefit in the bandwidth. The bandwidth cost has gone down by a factor of log p. Now let's look at the latency. This is not looking so good because I made this assumption that no communication is pipeline. So basically, I have to send a message to every other processor, p minus 1 messages. So p minus 1 times alpha. P alpha is a lot bigger than log p alpha, right? So this is a problem. And it's because I'm assuming that I have to wait for each message to each one of my neighbors to get there before I can go on to the next message. That's not how it works. Communication networks let you start all those messages up, and they all go in parallel. And so, in fact, if this communication is pipelined, you don't pay for p minus 1 messages. You only pay for the latency of the first one. So p minus 1 alpha goes down to alpha, right? I send it. So if I'm processor 0, I send a message to processor 1, immediately send the next message to processor 2, immediately send the next message to processor 3. They're all overlapping in the network. And that's assuming that my network is friendly to me. We'll get to that. But in principle, the lower bound is really just alpha. Okay? And in fact, if you make that reasonable assumption, this gets close to optimal. And there's a paper which says you really can't do any better than this particular algorithm. Okay? And I won't go into the proof or anything. Okay. So that is the best we can do, assuming the network behaves nicely. Now, a big chunk of the talk will also say when it doesn't behave nicely, and there's interesting tuning to do. But that's sort of the basic idea of the one-dimensional FFT. So are there any questions about that? Because that's sort of the end of that particular part of the talk. The optimal sequential FFT, where I have one processor, and I'm interested in minimizing the amount of memory traffic. And it's basically just going to be this algorithm. The sequential algorithm is going to mimic this algorithm. OK. So here is a theorem which says, what's the lower bound? No matter, if I take that algorithm and do it in any order, I can do all those multiplies and adds in any order I like, how much data do I have to move between DRAM and my cache of size capital M? And the theorem, which goes back a long time, says that no matter how I organize this algorithm, it's going to be lower bounded by some constant multiple of the number of arithmetic operations, m log m, divided by the log of the cache size. There isn't, so that tells me if I have a really big cache, it doesn't help that much, right? Because it's a log of the cache size. So this is really different from matrix multiply. Do people remember what it was for matrix multiply? The numerator was, again, the number of floating point operations. But the denominator wasn't log m, it was m to the 1/2. You can do a lot better with matrix multiply, lots more reuse. But there's just not that much reuse in the FFT. You only reuse each piece of data log capital M times. But anyway, so that's what we're going to try to attain. And that algorithm I just showed you, if we run it sequentially, we'll do it. Okay, so what do I mean by running that parallel algorithm sequentially? I'm just going to have a sequential algorithm which simulates what that did. So I'm going to pretend that I have little m over big M processors. Right? So why did I do that? Because that tells me each processor is going to own little m over p words, which is capital M. So basically, one processor is going to have all the words in its cache associated with it. Right? So it's going to do all the work of all the p processors one at a time. And it's going to use all of its data to store what's available locally. So every one of these FFT calls here, so whatever the green processor does there is going to be done by the sequential processor. It's going to gather all the green data and do whatever that green processor does. Then it's going to pretend it's the blue processor. It's going to gather all the blue data and do whatever the blue processor does. And it'll gather the pink data and the brown data. And then it'll do the same thing over here. It'll gather whatever the green data is and do whatever the green processor does. It's just going to loop through that picture. And And so that's going to do as little communication as this guy does, right? Because when it gathers the green data, it's going to go to memory. That's memory traffic. It's going to bring it into cache. It's going to attain the same bound. And so so every local computation is replaced by a similar phase working on cache resident data. So you just simulate the parallel algorithm. Now, this is sort of painful to write because you're going to have a different algorithm for every m, and every little m, and every capital M, right? This feels like a bad way to write code. But it turns out that if we do run the recursive algorithm, it'll actually do this for us automatically if we do the recursive algorithm correctly. And that's what the FFTW auto-tuner relies on, which I'll get to later. But I don't want to spend my time on the sequential optimization. I want to go back to the parallel case. But that's sort of the basic idea. So, okay, so let's see. Let me just sort of summarize everything about the parallel 1D FFT. The data comes out in bit reversed order, and then it gets undone when you do the inverse FFT, so that's good. So what about alternatives? I just want to mention one in passing that was invented quite a while ago now. It's due to Alan Edelman, and it uses a fast multipole method. So it sort of says you can think of each point on the unit circle, each root of unity, as points exerting gravity in a certain funny sense, right? And the fast multipole is about dealing with points exerting gravity. And he wrote down a way to do the FFT approximately, just like the fast multipole method is only approximate, that does much less communication. Okay, but the price is that you get an approximate answer. So this might be of interest someday. That's why I'm mentioning it. When problems get so big that it becomes communication dominated. So I'll just mention that in passing. Okay, so now let's go on to parallelizing higher dimensional FFTs, where the design space for how you do it is much more challenging. When people want to do like climate or quantum mechanics or whatever, they typically have higher three-dimensional FFTs because space is three-dimensional. And they're huge, and this is where the bottleneck is. So people are mostly worried about parallelism for higher dimensional FFTs. And so I'm going to sort of sketch what the ideas are, and then I'll sort of do a dive into a 3D FFT optimization. And just as there's a LinPack benchmark race that people do every year for linear equation solving, there's another race for FFTs. So anyway, so you can compete in this someday if you like. So as I mentioned before, what does it mean to do FFTs on something with higher dimensions? If it's a matrix, the 2D FFT says do all the rows in parallel and then do all the columns. Okay. So there are three obvious ways that I can imagine doing that. I could do a blocked layout. I could take my m by m matrix and have a square root of p by square root of p processor grid. Each processor owns a little square of m over root p by m over root p. And then I could do parallel 1D FFTs in each column and parallel 1D FFTs in each row. That's certainly a way of going about it. Here's a better way. I could use a blocked row layout. So every processor owns one piece of the rows, okay? And so the first processor owns m over p, the next processor owns the next m over p rows, and so forth. So now every row is on one processor. There's no communication. I do all the row FFTs with no communication whatsoever. But now, what do I do about the column FFTs? Well, I transpose the matrix. And then every processor owns a bunch of columns, and again, I can do serial FFTs. That's certainly one way to do it. And the third way to do it is, again, I start with a blocked row layout. Every processor owns a subset of the rows, so they can do sequential 1D FFTs in the rows, no communication required. And then I do parallel 1D FFTs in the columns. I leave the data where it is, but now each column is owned by p processors, so I have to do a parallel FFT. So these are all different ways you could imagine doing it, and it turns out that option 2 is going to be the best by doing the transpose in the middle. And the reason is, as we'll see, is that we can overlap communication and computation pretty dramatically. So while the transpose is going on, we can be doing other FFTs. So we're going to pretty much completely overlap the time it takes to transpose the matrix while we're FFTing other completely locally stored data. And so that's where the big benefits are going to be, except I'm going to show it all to you in 3 dimensions. Because that's where people have put most of the effort in doing it. So, and before I do that, I'm going to do a little dive now into hardware. And so to try to measure how much overlap of communication and computation is possible. And so, because transposes are expensive. So imagine that all you ever wanted to do was a transpose. There's no computation to overlap with. I just have a matrix. It's stored by rows across my processor. I want to make it stored by columns. So it's only communication. How expensive is that? And the answer is that's a problem, because if every processor tries to send its stuff to every other processor, right, because that's what a transpose requires, it's just going to totally overwhelm the network, because people don't build networks with that many wires in them, right? Everybody would have to be connected to everybody else in order to do a transpose, right, all in one fell swoop. And people, don't build that because it's, p-squared wires, right? They build simpler things like toruses, and stuff like that. And so we're going to be limited by what's called the bisection bandwidth. That's how much data can move from one half of the machine to the other half of the machine. And it's not going to be, everybody can talk to everybody. It's going to be much, much lower than that. And so that's why we want to sort of have this transposing going on overlapped with computation, because we're going to have to wait a while for this transpose to happen. So what I want to show you are some data measurements about what is the opportunity? How much time does it actually take to send a message so we can figure out what are the machine parameters that tell us what overlap is available. And so I'm going to use something called the log P model, which is a little bit closer to the hardware than the simple latency and bandwidth model, alpha beta model, that I've been using before. And so I'm going to show you sort of two simple versions of the log P model which try to capture what's really going on. So suppose processor 0 wants to send a message to processor 1. So the vertical axis is time. And so this axis says what's processor 0 busy doing, and what this vertical line tells me what processor 1 is busy doing. So when processor 0 sends a message, what does it do? There's some overhead. It's busy telling the network interface card to do something. So this green time is overhead spent by processor 0. It can't afford to do anything else. Then it's free. It can go do stuff. Then this L part is the latency in the network. So this is where the wires are busy sending stuff from processor 0 over to processor 1, and neither processor is occupied, so this is just the network. And that's time L. And then finally, when the message arrives, processor 1 gets bothered. It has to do something. And so there's some overhead on the receive side where processor 1 is busy, accepting the message, doing whatever is necessary. And depending on whether you have a network interface card, and depending whether it's MPI or UPC, there's different numbers here. Okay. So it's possible to measure all these things. It's interesting to construct the benchmarks. I don't think if there are questions about how to construct the benchmarks, I'll say it later. But all I want to say is, in this case, what is the potential for overlap? As soon as processor 0 gets to this point, as soon as its busy time is over, processor 0 can compute all the way from there to there, while this other communication is going on. So the potential overlap is from there to there for sending one message, right? So that's a fair amount of time. That's for sending one message. But what if we break up our one big message into lots of smaller ones and sort of pipeline them into the network? That's a slightly different scenario, and that's over on this side. So now what processor 0 is going to do, it's going to sort of pump smaller messages into the network as fast as it can. So here's the same picture as before. It's busy doing something, then there's latency, and then there's overhead on the processor 1 side. But there's something else called the gap. And the gap says processor 0 can't start the next message until it waits this amount of time. There's some buffer that needs to be emptied. So gap is the same thing as reciprocal bandwidth. So this is the time between messages. So the tightest that processor 0 can pack data sending over there is there he can send a message, then he can send one there, send one there. So the question is, what is the possible overlap in this scenario? And it's the idle time from the end of that arrow down to the end of that arrow. During this amount of time, processor 0 can do some computation. There's some overlap possible. Okay. So these are two different scenarios, lots of overlap to send one message, one big message, and maybe lots of littler times there where if you're sending it in smaller messages. So this is sort of a way to evaluate your hardware. It doesn't capture everything that the hardware properties of every network ever built, but it lets us try to measure things. Okay, so if we believe this picture, I'm going to show you numbers in the next slide, which measure all these things and give you a sense on a bunch of different networks and hardware how much overlap time is available. Okay, so I'm not describing the actual benchmarks, but it is possible to write little micro benchmarks that measure this stuff. So this is a Cray T3E with 3 different kinds of network interfaces. SHMEM, I don't remember what eReg is, MPI. An IBM machine with MPI and LAPI, which is sort of the one-sided communication interface. This is a Quadrix network, which has its own network interface cards, a MIRNet, and a gigabit Ethernet, all with its own different cards. And it's MPI versus something kind of lower level, where you can just send one message at a time. And for each of those platforms, we did this benchmark where we tried to measure all the numbers in this picture to send one message from there to there and measure all these quantities. And the green is the latency. That's the L term. The blue is the send overhead when the processor was busy sending. So there's the send overhead. The latency is that distance, and the receive overhead is that distance. And I should have labeled it with L's and O's and stuff. So there's the latency is green. The send overhead, O sub send, is blue, and the receive overhead is yellow. Okay, so this sort of gives us a hint of what overlap is possible. It's basically the green plus the yellow. That's sort of the time where there's a potential to do something else. And in some cases, green plus yellow is a fairly large chunk of the time. Now, this machine is a little weird. There's some hatch marks. What does a hatch mark mean? It sort of says that the log P model wasn't quite appropriate. So what it means is that this O send time overlapped the receive time. There was a point where the processor 0 and processor 1 were handshaking to one another to make sure that everything was okay, the message could be sent, and they were simultaneously busy sending the message because there was handshaking going on in the network. So that doesn't quite match this picture, but that's what was going on, and that's this gray time. So on the Cray T3E and MPI, there was a lot of handshaking going on. And so that time, there's no overlap there, right? Because both sides are busy. But otherwise, this kind of captures what's possible. Okay. So I think I've said, this just repeats what I was saying here, that which parts are overlappable. So we're going to be worried about overlapping communication and computation, right? Which is the green plus the yellow on the previous slide. Okay. And to do these, and I should also say that these vary so dramatically because people build different hardware in their networks. So some machines have DMA, direct memory access. So you basically have a little piece of the chip and you say, please move this data, and then the CPU tells it, please start moving this data, and then the CPU goes off and does something else useful like computation, right? And this engine is doing all the work, so there's lots more possible for overlap. And there's also the network interface card, which handles the network, and there's remote DMA, so that the same thing can happen on the receive end. So that would reduce the overhead on the receiver side to 0. Okay, all these possibilities. How are we doing on time? So what I'm going to do is compare GasNet, which is what sits underneath UPC. You've already kind of used this to do homework 3. This is the communication layer underneath that, and I'm going to compare it to MPI. So GasNet is particularly good for just doing one-sided communication. There's like no receive overhead. It just says, when you send a message, it just says, it comes, so when processor 0 sends a message to processor 1, it sends the data and the destination location. And when processor 1 gets it, its network interface card says, oh, I know where this belongs. I don't have to bother the CPU. I'll just put it where it belongs. And so there's lots less overhead involved there. And so for doing a transpose, where you know exactly where it's going to go on the other end, this is a particularly suitable way to do it. So let me give you some benchmark numbers to say how much faster GasNet is than MPI for doing some of these things. And then I'll show you the FFT times. Okay, so here's some advertising for GasNet versus MPI. And so the horizontal axis is the size of the messages. So we're going to send a megabyte. So all of these, we're measuring the time it takes to send a megabyte. But we're going to break it up into chunks of 16, 32, 64 bytes, right? And send as many of those messages as necessary to send a whole megabyte. So out here, I'm sending one whole megabyte all at once. And here I'm breaking it up into 2 half megabyte chunks and 4 quarter-megabyte chunks and so forth. And the vertical axis is bandwidth, so up is good. And once I'm sending very large messages, I'm sort of hitting the peak of the network. And so whatever that is, 800 megabytes per second, I think that's, yes, 800 kilobytes per second. This is old data. So that's how fast it's going. And the blue line is GasNet, and the red line is MPI. And when it's large enough, they both sort of do a pretty good job of getting maximum. But remember, what we want to do is send a lot of small messages so that we can overlap communication and computation. I want to send a message, compute, send a message, compute. So now there's a difference. I'm going to be sending small messages. I'm going to be down here. And down here, where I'm sending 1,000, 1 kilobyte messages, I'm going twice. GasNet is going twice as fast as MPI. So here, there's a lot more opportunity for overlap, and the messages will get there a lot faster. So this is going to, so it's operating down in this region where there's going to be an opportunity to get a lot more benefit out of GasNet. If I only send huge messages, it doesn't matter. But if I send lots of small ones to be able to overlap, I'll be down here, and there's a payoff. OK, so numbers. So here, I'm sending my whole megabyte, and I'm sending it in 4 kilobyte messages. So I'm down here where I'm sending fairly small messages. And the blue line is how fast MPI is going as a percent of peak. So 100% is very good. And the red line is a percent of peak for GasNet. And it sort of uniformly does better on all of these different platforms. So a LAN network connecting an alpha, a LAN network connecting Itanium 64s, all these different platforms. The last machine is a shared memory machine. It's kind of hard to get data. What does it mean to do message passing on a shared memory machine? It works, but the interface doesn't quite make sense. So you can ignore the last column. But in all the other ones, you're getting a serious benefit by doing this kind of communication. OK, so what I want to do now is do the 3D FFT and optimize it very well and compare how well you can do with MPI versus how well you can do with GasNet. So we're going to use the NAS Fourier Transform benchmark. So the NAS benchmarks are these standard benchmarks that people produce to measure how fast your machine is, and they have lots of different things inside of it, kernels, the Fourier Transform being one of them. And it's going to be a 3-dimensional one. I'll show you a picture on the next slide. And typically on most machines, you're spending 30 to 40% of your time doing the transpose in the middle. So there's a lot of room to improve that. There's a lot of benefit if you can make that 30 to 40% be smaller. And so the assumption is I'm going to have a 3D grid of data. And a 3D FFT means I do the FFT and all the one-dimensional things in the x direction, then the y direction, then the z direction. And the assumption is I'm going to partition it so that into slabs. It's a one-dimensional partitioning, picture on the next slide, of this 3-dimensional bunch of points. And so, and this particular project, which did so well, started as a CS267 project a few years ago. OK, so here's the picture. I have this grid of points, nx by ny by nz. I want to do an FFT, a 3D FFT. That means on each vertical piece, then each horizontal piece, then each piece going into it. And my assumption is I'm going to have a 1D partition, which means that processors 0 through 3, each one owns this 2-dimensional slice. That's going to be the starting point. OK, so the question is, how do I do my 3-dimensional FFT? And it's pretty clear that I should do all of the, if I just look at what I own, what can I do without any communication at all? I can do all of the FFTs in the vertical direction with no communication. I can do all of the FFTs in the horizontal direction. It's only when I go into the cube that I'm in trouble. So step 1 will be do all the FFTs on each column. That's purely local. Do all the FFTs in each row. And now I have to do the last phase. And now communication is necessary. So what do I have to do? I have to transpose it so that everything is local. And so what I need to do is change my layout from this particular one to this particular one. And so now everything in the sort of inward direction is stored locally in a processor, and I can do all local FFTs. So the question is, how do I best overlap the communication required to get me from there to there with all of the computation of the FFTs? So I have a pretty big design space. And so there are a lot of ways that I can do that kind of overlap, depending on how I break up those slabs into pieces and do FFTs and communicate. So there's basically 3 different, obvious ways to do it. I can finish the entire FFT of the entire slab and transpose it all in one fell swoop, so the least amount of overlap. But that's the simplest thing to do. In other words, I would finish all the FFTs on this and then do the transpose. There's another approach where I called slabs, where I will only do part of that chunk here. I'm going to only do a little piece of it and then start transposing it while I go on to the next part. Right? And how much of it will I do before I start transposing it and then go on to the next part? It'll be called a slab, picture to follow. And then I can break it up into lots of tiny little pieces called pencils, one-dimensional things. And I will do a pencil at a time and transpose a pencil at a time. So there'll be lots and lots of tiny little messages, but there's possibly more opportunity for overlap. And so as I go from packed slabs to pencils, I'm going to increase the number of messages by an order of magnitude, because I'm sending there are a lot more tiny little pencils than there are packed slabs. But each message is going to be proportionally smaller. I'm sending the same amount of data, just different numbers of messages. And so let me draw some pictures now and show you what it looks like. So I'm going to draw every last detail for a 16 by 16 by 16 cube with 4 processors. So let's look at processor 0. It's going to own 4 16 by 16 slices. So here's a picture of all the data owned by processor 0. So what can it do? It can certainly do all of the work on each of these one after another. It does all of the row FFTs. This is all 16 times 4, all 64 row FFTs. Then it can do all 4 times 16 column FFTs, right? So now I'm going to send, now I got to transpose. So what I'm going to do is I have to break up all of the parts. I have to figure out which goes to processor 0, which part goes to processor 1, which part goes to processor 2, and which part goes to processor 3. And then I'm going to pack them all into messages. So everything that goes to the green processor, I got to pack together into one message to send to processor 0. Everything that goes to processor 1, all of the orange stuff, I pack into one message and send it to processor 1. So this is the packed slab version. This is sort of the send as few big messages as possible. And so there's, in this case, there's 4 messages. And then for the benchmark, where I have a 512 by 512 by 512 grid with 64 processors, I'm going to send 64 messages of that size each. Actually, I'm not sending a message to myself. It's really only 63. But basically, that's the idea. So this is the least possible overlap, but the fewest number of messages. OK. So if I do that, I only get 67% of peak bandwidth. So this is not a particularly good, this was an Opteron InfiniBand. So it was, there's just too much congestion. Every processor is trying to talk to every other processor at the same time. I'm totally overwhelming the bisection bandwidth of the network. And it wasn't a good idea. OK. So I'm not getting the peak speed of the machine because of the congestion. So let me try the next option. And so here's the idea. Here is one of my 4 planes. I'm going to go back to my 16 by 16 by 16 grid. And so I own 4 of them. There are 4 processors. And so this has to get transposed. So I'm going to start by doing all the column FFTs. OK, so I'm going to finish doing all the FFTs in the columns of all of the processors. And so now I'm going to do all the FFTs on those rows. So this stuff is eventually going to have to go to a different processor. This is going to go to the green processor. This is going to go to the orange processor. So the idea is I finish all the columns. Then I just finish those rows, and I start sending them to processor 0. Well, I send those to processor 0, I do all the orange rows. So there's the overlap. The green stuff is going to processor 0, overlap with FFTs of the orange rows. As soon as I do those, I send those to processor 1 and start doing the FFTs of the yellow rows. So I get overlap between that communication and that FFT. And then there's a pipeline. And I send the yellow stuff to processor 2. I do the FFTs of the blue rows. And then I put that to processor 3. And then I start the next plane. And there are 4 planes. So I pipeline all of these slabs. So for 512 cube grid, I'm sending lots more messages than I had before. I had 64 messages before. Now I have 512, but they're proportionally smaller. I'm sending the same amount of data. OK, So that's slabs. And once you've seen that idea, it's kind of obvious that I could do this at a much finer granularity called pencils. So again, I'm going to finish all the columns, get them all done. And now I'm going to do, so here is the destinations. So this stuff is eventually going to be sent to processor 0, to processor 1, and so forth. I'm going to do the FFT of that row and immediately send it. And as soon as that starts sending, I'm going to immediately start doing the FFT of the first orange row, and I'll send it. So you see, I have these two messages in flight, but they're going to different places, right? That's going to minimize congestion. I'm sending a little message to 0 and a little message to 1. So hopefully the network will not be so unhappy. And then I do the first yellow row, send that to processor 2, the first blue row, send it to processor 3. So now I have all these messages in flight to different parts of the network, and I just keep going, right? Just sort of cycle through it all. And that's so now I have all this other opportunity for overlap. Hopefully, between and then I do it for the next plane. Okay, so now if I go back and say, how much have I actually done here for my 512 by 512 by 512 grid, I've sent a heck of a lot more messages, 4,000 messages, but they're pretty tiny. But this was a sweet spot, remember? 8K was a pretty good size for GasNet. It got pretty much half a full machine bandwidth. Okay, so those are the algorithms. And so now it's time to show you data about how well it does. And so let me sort of just show you some. This isn't the algorithm yet. This is just showing what to expect. So here again is this benchmark where I sent a megabyte of data broken up into 16 size point messages, 32-word messages, 64-word messages, all the way up to one enormous message. And I'm comparing the bandwidth, the vertical axis is bandwidth, of GasNet versus MPI. And I want to predict what's going to win. So if I do the packed slabs where I send one large message, my message is going to be of this size, and GasNet and MPI are going to run about the same speed. They get about the same bandwidth. If I do slabs, more small messages, I'm going to be right around there. Message size is going to go down, and there's still not that big of a gap between the speed of MPI and GasNet. But if I go down to pencils, and I send lots and lots of these tiny messages of size 8K, that's how fast GasNet's going. It's getting almost full bandwidth, and MPI is doing much, much worse. So now I'm getting I have the potential of having full network bandwidth, but with a lot more overlap than I would with MPI. Okay, so this is sort of contrasting MPI and GasNet. So now benchmarks finally for lots of different machines. So this is just for reproducible science. It's all the details of how the experiments were done. You don't have to read it all. There was an old NERSC machine called Jacquard, a bunch of opterons connected on InfiniBand, a bunch of alphas connected on an ELAN 3 network, a bunch of Itaniums connected on an ELAN 4 network, and then a bunch of Pentium 4s connected over MirrorNet. So just lots of different configurations. So we will show you the data. And so what is the data? When you download this benchmark, they actually give you a version in Fortran running in MPI. So that's going to be sort of the baseline where we run. And that's going to be speed 1. Okay? And then we're going to compare that to UPC. So it's written in C. You've written UPC code, using the 3 different kinds of communication. Packed slabs, which the fewest, biggest messages, slabs, the medium-sized messages, and pencils, the most small messages. And the vertical axis, up is good. It says how many times faster is it than the baseline Fortran plus MPI code? And the answer is, about twice as fast. And up is good, so pencils beat slabs, beat packed slabs, as kind of predicted. And yeah, it was 1.9 x speed up. So how much time was actually spent in communication? So now we're comparing UPC, slabs, pencils, versus MPI, slabs, pencils. So now this asks the question of how much it's worth doing UPC instead of MPI. And you can see that vertical axis is time, so down is good. And the first 2 colors are UPC, and the last 2 bars are MPI. And you can see that UPC wins. So it was definitely worth going from MPI, these 2, down to there. So there was definitely an improvement by using GasNet instead. And there's a bar missing here because MPI crashed when it was trying to do the pencils. There were too many messages, and it just couldn't handle it. OK. So here is one more kind of summary on the, again, for all these different platforms. So this was the best, Fortran plus MPI code, megaflops per processor, up is good. And here was the best MPI code, which was always slabs. And here was the best UPC code, which was always pencils. And so you can see that there was definitely a benefit to doing it this way. So this is sort of fine-tuning, but there was definitely a payoff. So a few more platforms, just to bring it to a close here. So this was the FFT performance on Blue Gene P, and as a function of the number of cores. And again, comparing MPI with pack slabs, which kind of gave up at 16,000 cores. And there was pack slabs and slabs with certain kinds of special collectives for doing the broadcasts, for doing the transposes. And that was definitely better. It was about a 17% payoff. All right, so it's not enormous, but it was a good idea. So that was on a Blue Gene. And finally, one more. This is a Cray XT4. This was an older, this was Franklin. Yes, this was the Franklin machine. And the horizontal axis is the size of the benchmark. And D is a 2K, three-dimensional FFT. And there, double all the dimensions, quadruple, excuse me, octuple. And then these are problems of smaller sizes. And it's comparing, again, MPI pack slabs, UPC pack slabs, and UPC slabs. And once the problem is large, UPC slabs wins. But on this machine, it was actually better to do MPI pack slabs. And I asked why this was. And they apparently optimized the network to help MPI send this particular size message. So it was not a benefit to do it this particular way. So it's hard to sort of make global claims depending on how people build their networks there. OK, so that is the end of three-dimensional FFTs. And I have just a few slides about FFTW, what it does to do auto-tuning of sort of sequential one-dimensional FFTs, just a few examples. But are there any questions about the parallel 3D FFTs before I go on? OK. So FFTW.org, the fastest Fourier transform in the West. And it's very similar in spirit to some other systems I've told you about. We've talked about OSCI and its predecessor, sparsity, which is trying to search over all reasonable algorithms for doing, this was case, sparse matrix vector multiply, and these were dense matrix multiply. And it's pretty widely adopted. A lot of the libraries that people put out there, on various machines, the ones you would use at NERSC, are built this way. So they've done a very good job in tuning. And I will be using their slides. So it does real and complex FFTs of arbitrary size and dimensionality. And basically, you tell it which size you want. It will give you a custom FFT for that size that is particularly fast. It does lots of automatic code generation. Almost all the code is automatically generated. OK. So here's some performance. And on lots of different platforms. And this is double precision, complex FFT for only power to show you. And the blue line at the top is, this is very hard to read, is FFTW and out of place. So that's where, so when you do the FFT, you have a choice. You can either overwrite the input vector with the output vector, that's in place. Or the output vector can be a new vector. So y equals f times x. Y does not overwrite x. That's out of place. And the top two curves are those two slightly different ones. It's pretty clear that if it's in place, there's less data movement, and you have more opportunities to reuse cache, because you're using half as much storage. So in place, which is good enough for many applications, it has those two versions in it. And that gives you the top line. And what are all these other curves? Well, people have written a lot of FFTs over the years. And so all of these curves are different ways people have attempted to write FFTs with different levels of optimization. And the whole point of this is to say it dominates, generally, all the other ways of doing FFTs. So these are all powers of 2. It works for non-powers of 2. And obviously, the algorithm I told you about with divide and conquer, and everything was assumed to power of 2. You got to work differently. And it handles all those cases. And you get the blue line at the top. And most other people don't bother, right? Because there's just too many ways of doing it. This is why it's worth automating. So everybody else goes significantly slower. And they do work as hard as you normally would. And the other thing is that if you do SIMD, it's easy to put that in. That's particularly tedious for the non-power of 2 case. But that's all inserted automatically, and it's tuned as to what the alignment should be. And again, the claim is that if you look at the blue line at the top, then this greatly dominates the other folks because it's because they can do the SIMD code as well as doing a good job with divide and conquer for non-powers of 2. Okay, so that's their advertising for that. So what are the steps here? So there are many ways to do an FFT. In fact, over the years, I think about 100 papers have been published on different divide and conquer algorithms. The one I showed you, the classical one, there's 100 others. And so there's a lot of different design choices you could make, and you can do a different divide and conquer at every level, right? And especially if your number n is not a power of 2, you may have to use a different divide and conquer at every level. And so it searches over many of those different possibilities. And that takes a while. It builds a plan, and it stores it. So what you do to run this is you say, please build a plan for the best way to do an FFT for this particular size. And it stores that in a file called wisdom, its words. And then when you actually want to call it at runtime, it just goes and gets the plan and runs it, and it's very fast. And then in the base case, it has this very fast automatically generated code. So here's what your code would look like. You declare something called a plan, which is a rather complicated data structure, kind of opaque to you, which keeps track of how it all works. And then you say, please plan my one-dimensional FFT of this particular dimension, where it overwrites itself, and it's the forward FFT as opposed to the backward one, and I'm not sure what measure refers to. Okay. And then when you actually want to run it, you can just execute the plan. Okay. And when you're done, you can throw it away. And the reason that you're willing to pay this price, because it's a significant overhead to build a plan, is you're probably going to do a lot of FFTs over and over again for the same size, so it's worth paying that overhead. So in order to deal with the minimizing communication, what they do is that they do recursion. And they take into account the fact that they can minimize communication naturally just by doing divide and conquer and evaluating this tree. This is the same divide and conquer tree that I showed you before, and evaluate it by doing depth-first search on the tree. So they make the point that a traditional algorithm would sweep over all of the little butterflies of size 2 at the bottom, then do all the butterflies of wingspan 8, then all the butterflies of wingspan 4, and then all the butterflies of wingspan 2, and they'd pass over all the data log n times, and the communication traffic would be n log n, no reuse whatsoever. But they point out that if you do, let me just scroll ahead here, if you just do natural divide and conquer depth-first search on this tree, let recursion run the way it normally does, once it fits in cache, you never leave it. And it will get automatically reused built in for you, and you don't have to sort of tune it to every different cache size. And sometimes that pays off very well. It doesn't work for every algorithm. Here it works out very nicely. And so every size just stays in as soon as one of these boxes fits in cache, there's no more traffic. Yes. So, and this is just saying, cache, this is called a cache oblivious algorithm, just depth-first search, divide and conquer. There's a famous paper written back in 1999 that said this works very well for many different algorithms, and we've seen it before too. And let me just skip ahead to one more slide to summarize one other project. This is a project at Carnegie Mellon for generation not just of FFTs, but for a very large class of digital signal processing algorithms, Viterbi, convolutions, you name it. And at one point they had, I'm not sure how complete it still is, a web page. You could say, I want this particular signal processing algorithm for this particular problem size and this particular hardware. Give me the best algorithm, and it would hand it to you. They now have a startup. You can imagine it's a rather good idea. And you can learn more about it at this particular website. There's still a lot of work. And so we have now, at this point in the semester, it's a good time to stop, pretty much completed all of the different dwarfs that are associated with high-performance computing. We've also done graph algorithms. And so that was the plan, to sort of complete all of those. We didn't do every last interesting possible dwarf, but we did many of them. So what does the rest of the semester look like? I'm going to do dynamic load balancing next time because we talked about static load balancing quite a bit. That's graph partitioning and its variations. There's a bunch of different techniques that have to do with dynamic load balancing. Then we're going to have a lecture on, next week, we'll have a lecture on computational astrophysics because several Nobel Prizes recently to show for that work. And what are their parallel processing algorithms? That's largely big data is what they're being driven by. And then the very last lecture will be by another national lab person talking about the materials project, where they again have large amounts of data on sort of the chemical properties of potential new materials and how they mine that data to decide which new materials they want to build. So, and that will bring us to the end of the semester. Yes, question?
So when is the project presentation due?
So the plan is that I would like to use this room for everybody to give a 1-minute poster summary, which we will record for posterity, because it's sort of good for other people to see what all the different options are. And assuming you're all willing to stand up here and do that. And then we'll have the poster presentation out there and free Pete's coffee if I can arrange that or something. So. And that would be in this, so in this location at the same time as the regular lecture would have been on the last lecture day of RRR week. Thursday. That's Thursday, right. The report itself will be due later.